is this taking so long? There's only 500 trillion elements in this sorted list. Why does it take so long to get the largest element in this list? Oh my god, my computer's gonna explode!
What's wrong with you?
My code is slow, man. You guys help me debug?
So tell me, why are you even iterating through the large number of elements in this list to find the largest element? You do realize the list is sorted, right?
Yeah, there's an easier way to do it in constant time.
What is constant time? I'm not too familiar with pop culture references.
Don't worry, we'll explain.
Since this is sorted, we can easily access the largest element at the end of the sorted list. This will always be true with any sorted list, making it constant.
O1 to be exact. Now that we're here, we can help you understand the different time complexities.
So for this first time complexity that we are looking at, it is O1 or constant time. And an analogous example that I can provide here is that imagine we have a backpack that you put your necessary items in for school, for example. And no matter how many of these items that you put in, you're looking to instantly retrieve some item in this backpack without needing to search. So regardless of the amount of items that you have in this backpack, the task of retrieving just some random item will always remain constant. It's not dependent on the amount of items that we have in this backpack, right? So let's say we had like 3 items in this backpack, but we just want to retrieve like a random element or a random item in this backpack. And we end up getting the apple, right? So regardless of what's in our backpack and how many items are in our backpack per se, the task of retrieving just one random item will always remain constant. It's not dependent on, as I said earlier, the number of elements that we have in this backpack. So the proper definition of O of 1 is that the time it takes to perform a specific task, regardless of the size of the input n, will always remain constant. So we see as n increases, the execution time remains constant. It doesn't, have some sort of pattern. It's not linear or anything. It just remains constant, right? I'm going to provide an example. So let's say you're curious about retrieving an 80-second element of the 500 element list. So here we defined a list of 500 elements that's randomly shuffled. And you can see that the length of the list is 500. It's possible that we can iterate through the list 82 times to get the element, but that's costly in terms of time complexity. And instead, we can simply index the list to retrieve the 82nd element, right? And in Python, that would be the 81st index that we would have to use, as indices are 0 indexed. We know that indexing is O of 1. And as a result, that gets us the value of 281, which means that that is the 82nd element in this 500 element list. I would like to provide another example. This is a function that I define called constant underscore time. So let's say the size of our input n is 100. Some large input n, right? And we see that in this function, we have a for loop using the range function from 0 to 10, meaning that this will only run for a total of 10 times. And for those 10 times, we're going to be decrementing whatever n is at that iteration by 1. And then we're going to return n. So will the amount of times we run this for loop change if n were to be 500? No, right? It's always going to be 10 times. So this function, or the for loop in this function, is constant because it only runs for a set amount of 10 times regardless of the size n, or O of 1. And the operation here, n equals n minus 1, we know that when we perform arithmetic operations, that's also O of 1. It's not dependent on size n. The time complexity for this function is O of 1, maintaining constant time. So the next time complexity that we will be looking over is O log n. And an analogous example that I want to provide is that imagine that you have a phone book with names that are sorted alphabetically. and you're looking for a specific name, but you decide to do so in a more efficient manner. So, you open the phone book to the middle and check if the name that you are looking for comes before or after the page located in the middle of the book. If the name comes before, you repeat the process for the first half of the book. Likewise, if the name comes after, you repeat the process for the second half of the book. And you continue to repeat this process until you find the name. So, essentially, with each step in this process, you're eliminating half of the remaining pages that are needed to search through, which makes sense with log mathematically, which leads to our proper definition. So, with O log n time complexity, it means that as the size of the input n grows, the time that it takes to perform an operation increases logarithmically. And this is achieved by dividing the input size in half with each step, which leads to a reduction in the number of steps required as n grows, which is kind of similar to the analogous example that I provided earlier. If I were to provide an example, we have a function here, which takes in parameter or input n, and inside this function we have a while loop, and the while loop, we see that its conditional statement is dependent on input n. This while loop will run as long as the conditional statement that n is equal or is greater than 0 is true. So within this while loop, we're essentially dividing n by half. And we know that our n is our input, and the iterator variable n that we're using in our while loop is dependent on our input n. We keep doing that until n becomes less than or equal to 0, so it's not greater than 0. So each iteration is effectively cutting this value of n in half, and it takes a logarithmic number of steps to reduce n to 0. So if we were to pass in a value of n, which is equal to 16, as I've done here, we see that for each iteration in the while loop, our n gets halved each time, for a total of 5 iterations, which makes this whole time complexity of this function O log n. That's because with each iteration, we're dividing the input size by 2, leading to a logarithmic time complexity. So the next time complexity that we will be looking over is O of n, or linear time. And an analogous example that I would like to provide for O of n is that imagine you are a chef who's preparing ingredients for a recipe, and you have a list of n ingredients that you need to go through one by one in order to prepare them. And as you move through this list of ingredients, you handle each ingredient once to prepare. And the time that it takes to prepare all ingredients is directly proportional to the number of ingredients that you have. So if you were to double the number of ingredients in this list, double the time it would take to prepare all of these ingredients, right? So that leads to our proper definition, whereas O of n is linear time complexity, which means that the number of operations required to complete a task grows linearly with the size of the input. So the runtime of our operations increases linearly or proportionally with the size of our input n. Now, if I were to provide an example, our for loop is dependent on the size of our list nums. So this makes this for loop O of n. And we know that creating a variable that just takes in an empty list is O of 1, and appending a value, which takes O of 1 time. And returning something also takes O of 1 time. It's not dependent on n. Since the number of times we run the for loop is directly proportional to our size of the list nums, O of n takes precedency over O of 1, right? And since these are all O of 1, the worst case scenario, or just the time complexity of this function, is O of n, or linear time. The next time complexity that we will be looking over is O n log n, or linear arithmetic time. And an analogous example that I would like to provide is that imagine that you are a contestant for a competition who has to compete in a number of challenges that have to be completed under a certain time constraint. For each challenge that you progress through, the difficulty becomes half as hard as the previous one, meaning that the competition becomes easier as you progress. So, although each challenge requires a certain amount of time to complete, the overall difficulty is halved, meaning that the competition difficulty decreases logarithmically as you advance. So, the proper definition of O n log n is that for n times, log n operations occur. And this is similar to our example where for each challenge of an n number of challenges, each challenge gets easier in terms of difficulty, as it only becomes half as hard as the previous challenge. We have a function defined, just called time underscore complexity, which takes in an input n. So we have two loops. We have a for loop and a while loop. And our for loop is our outer loop, which iterates 5 times n plus 1 times, where n is the size of our input. We know that n is dependent on our input. This means that the number of iterations of our outer loop grows linearly with n because it's directly proportional to our input n. So the time complexity contribution from the outer loop is O of n, right? For each iteration in our outer loop, we have a while loop that we have to execute. And for this while loop, we define j equals n, which is O of 1. And this while loop will run given the conditional statement being true if j were to be greater than 1. So each time this while loop is run, we're essentially halving j, and the number of steps it takes for the inner loop to complete would be logarithmic, right? With respect to n, because j is equal to n. So, therefore, the while loop here would be O log n. And when we combine the time complexities of the outer and the inner loop, or our inner loop is dependent on our outer for loop, we can just multiply the complexities together. We would get the time complexity O n log n.
Next, we'll be going over time complexity O of n squared. An analogy that can help understand this time complexity is to imagine you are at a cooking competition. There are two teams, Team Sweet and Team Savory. Each team has n chefs, and each chef specializes in unique dishes. So to try out different combinations of unique dishes, each chef from one team needs to pair with every chef from the other team. So each of the n chefs from Team Sweet needs to pair up with each of the n chefs from Team Savory. This will create n times n, which is n squared pairings. As the number of chefs increases, the number of interactions or the number of pairings grows quadratically. So to properly define, O of n squared is a quadratic time complexity. This means that the number of operations required to complete the task grows quadratically with input size of n, and this is faster than linear growth. Let's take a look at an example. Let's say we create a function that finds all the numbers that are duplicated in the input list. To do this, we want to use two loops. The outer loop loops through every number from the input, and the inner loop compares the number at index I from the outer loop with every other number after, and this will run n minus I plus 1 times for each outside loop variable I. Since the outside loop will run n times, the total time complexity would be O of n squared. The next time complexity we'll go over is O of a to the nth power, where a is greater than 1. An analogy that can help understand what this growth is to imagine that there is a magical plant in your backyard that starts off as a small seed, but each day it grows exponentially larger. After a week, the magical plant grows exponentially and covers a small area of your backyard. After a month, it takes over the entire backyard. And after a year, it may tower over the entire town. In this example, A represents the growth rate of the magical plant, and N represents the number of days. To properly define, O of a to the nth power is an exponential time complexity given when a is greater than 1. This means that as the size of input n grows, the time it takes to perform a task increases exponentially. In other words, the number of operations required grows exponentially with the size of the input n. Let's take a look at another example. Let's say we create a function that calculates the nth Fibonacci number. A Fibonacci sequence is a series of numbers where each number is the sum of the two previous ones, such as this sequence. Let's look at this graph here to visualize what the code is doing. Our first function called Fibonacci 4 will return two recursive calls, Fibonacci 3 and Fibonacci 2, which will each return two recursive calls. Fibonacci 3 will return Fibonacci 2 and Fibonacci 1. Fibonacci 2 will return Fibonacci 1 and Fibonacci 0. This process continues until it reaches the base case, which is n is less than or equal to 1. Although the size of our input n is fairly small in this case, from this graph we can see the pattern that as we go down further in the graph, the total number of recursive calls to function Fibonacci increases exponentially. In this case, the time complexity is 2 to the nth power. The last time complexity we'll look at is O of n factorial. Factorial time complexity is often encountered in problems involving permutations. Imagine you have 3 books, book A, B, and C. You want to arrange them on a shelf and you want to know how many different ways you can do this. You can start by choosing either A or B or C. Let's say you pick B. After placing the first book, you only have 2 books left to pick for the second position. Let's say you pick A. Now for the third position, you have no other choice but to choose the remaining book, which is book C. This is just one combination of the many ways you can arrange the books. Since any book can be in first, second, or third position, the total number of ways to arrange this will be 3 for the first position times 2 for the second position times 1 for the last position, which is equal to 3 factorial, which is equal to 6. This example can be expanded to any number of books, and the number of arrangements grows factorially with the number of books. To properly define, O of n factorial is a factorial time complexity, which occurs when the number of operations increases factorially with the size of the input n. This means for any input of size n, the number of operations is n times n minus 1 times n minus 2 times all the way to 1. This code illustrates the analogy I just mentioned. If there is only one book, there is only one arrangement possible. If there are more than one book, the code tries each book, which is book at index I, for the first position, and recursively calls itself to generate permutation of the remaining books. Here, the input here skips the I element, which means it is looking at all the ways to arrange the rest of the books. The execution time of this function will grow factorially as the input size, which is the number of books, increases.
Now that we've gone over all of the time complexities, here are a few tricky questions you might encounter on exams or in your work in general. Suppose you encounter this question on an exam with no other context. If you see a problem that you think is too challenging to take on, it often helps to trace through all of the components to really understand the purpose of your code. The first line of code here is a function definition and a header where the function is simply named and the parameter is organized. So it has a time complexity of O of 1. Next, a variable max height is initialized to a value of negative infinity. Since this is just the code for how you'd write negative infinity, it has a time complexity of O of 1 since a variable is just being initialized. Below it, n is also being initialized, but I urge you to keep your eyes out for built-in functions that are being used, such as len. Len has a time complexity of O of 1, and if you wanted to know why, it's because every time the length of a list changes, the length is being updated and stored internally, so you don't really need to iterate through all of the elements in the list to count its length, but rather all you need to do is access it in a constant time operation. So the line with n has a time complexity of O of 1. Next, we encounter two for loops. The first one iterates through a range of n, or the length of the numbers list, and the second one iterates through a range of n plus 1 to n. As you can see, while the outer loop always iterates n times, the number of times the inner loop iterates changes as n changes. For example, when I is 0, the inner loop iterates n minus 1 times, but when I is 1, the inner loop iterates n minus 2 times. Since the number of iterations of the inner loop depends on the outer loop, we call the inner loop the dependent loop. In order to find the time complexity of these two loops, you would need to use the formula for an arithmetic sum, which is n times n plus 1 divided by 2. So the time complexity would be O of n times n plus 1 divided by 2, which can be simplified to O of n squared. So inside the for loop, the input list is being indexed by the I and j iterator variables and then being added together, which, as we saw before, has a time complexity of O of 1. Next, the sum function is being called on numbers. While at first glance, it's easy to think that this line will have a time complexity of O of 1 since there are no apparent for loops, that is not true. If you think about what the sum function does, it iterates through all of the elements in a list and adds them together. That is why this function will have a time complexity of O of n instead. The built-in functions like min and max also act in the same way, since they iterate through the entire list, comparing the values in order to find the min or max, respectively. Finally, there's a simple if statement comparing two values and an assignment statement inside the if statement, both of which have a time complexity of O of 1. If we were to sum up all the time complexities we've covered here so far, we'd get this, which simplifies to O of n cubed, which is the time complexity of this problem. Now let's take a look at an actual exam question from the fall 2019 midterm related to time complexity. This question is asking what the time complexity of this function is, a function that we can see returns a map object, where the lambda function is applied to every element in the list, squaring the elements. As we saw earlier with the sum function, since the lambda function is applied to every single element of the list, it would at first glance make sense to also think it had a time complexity of O of n. However, we must keep in mind that what is returned isn't the new list with the changed elements, but rather an iterator. As discussed in class, when a map object is created, the lambda function isn't immediately mapped onto all of the elements. It only applies the mapping function to the next element whenever next is called on the iterator, which is why its time complexity would be O of 1 instead. It's only when a list is called on the map object that the lambda function is applied to all of the elements and a time complexity of O of n is achieved, as seen in the following practice exam question. As a side note, filter works in a similar way, where the filter object being returned has a time complexity of O of 1 since only the iterator is returned, but a list being called on the iterator has a time complexity of O of n. For our final question, we're going to look back at question 1, except let's say we add another variable temp, assign it to 150, and add an if statement to the bottom of the inner for loop. Will the time complexity change even though the if statement and temp variable we added by themselves have a time complexity of O of 1? Well, the time complexity will change, which is why it's important to look at the question as a whole as well as the individual parts. Now that the temp variable is added inside the outer for loop, initialized to 150, every time the inner for loop runs, 50 will be subtracted from temp. However, the if statement states that if temp is ever less than or equal to 50, the inner for loop should break, meaning that the inner for loop will only run 3 times or less every time, so at most 3 times. This is why the time complexity of the inner loop will be counted as O of n, as a simplification of the 3n complexity gotten from the sum being called in each iteration of the outer loop at most 3 times, making the overall time complexity now O of n times 3n, which as a simplified time complexity is O of n squared instead of O of n cubed.